Chapter 16 is a discussion of thermodynamics, which, depending on where you are in your physics education, may come with a lot of familiar ideas. But as we proceed through Chapter 16, we'll see how these things relate to the world of chemistry. You'll notice as you go through Chapter 16 that I've pulled out some key ideas from this chapter. Not everything that's discussed in the textbook appears in the lecture slides. Okay, so if that's the case, like microstates, for example, you can assume that that's something that wouldn't be tested. Again, if it appears in the textbook but not the slides, then it's okay to not worry about studying it, and not to say that it's not important. And for Chapter 16 here, we'll probably have 2, maybe 3 videos, depending on pace. Okay, so what's our schedule looking like? Today, in this video, we're going to talk about spontaneity and entropy, and then later on discuss the second and third laws of thermodynamics, and finally Gibbs free energy. 2 huge important variables now that are introduced in Chapter 16. Way back in Chapter 5, we learned about delta H, right, a discussion of enthalpy. But now we've got entropy in 16.2, which is delta S, and then finally Gibbs free energy in 16.4, which is delta G. Okay, so G, H, and S, 3 variables that'll be important in a discussion of thermodynamics. Okay. Definition of thermodynamics up top here. That's study of relationships between energy and work associated with both chemical and physical processes, which is a definition that may sound familiar. It's pretty similar to what we said in Chapter 5. Okay. But where we're going now is thinking about, right, 16.1 is all about spontaneity. Thermodynamics allows us to determine if a process, right, a chemical process or a physical process, will occur spontaneously under the specified conditions. Because in the world of chemistry, we can make anything happen with inputting enough energy into the system. Okay? But what we're concerned with now is, will it happen spontaneously under the given conditions? Okay? And there are only 2 possibilities, right? It either works or it doesn't work at whatever pressure, temperature, etc. that you're considering. Okay? If a system is changing, it's spontaneous in one direction, right? It's non-spontaneous in the other direction. Okay? So it's either spontaneous, it happens naturally, or it occurs by force. We have to make it happen, which can only happen by putting energy into the system. Okay? So if you've got a piece of paper in front of you, you're jotting down notes, what you want to keep in mind, draw an arrow one direction, right? Anything that's spontaneous in one direction is non-spontaneous in the other direction. Okay? So under, right, the conditions that are outside right now, water flowing downhill, okay, that is a spontaneous process. Water flowing uphill, the opposite thing, is non-spontaneous. Okay? Assuming it's above freezing, where you are right now, ice melting is a spontaneous process. Okay? Ice freezing is non-spontaneous. And keep in mind, in Chapter 12, we discussed kinetics. Okay? Thermodynamics and spontaneity is totally different from kinetics. Okay? Thermodynamics is just, will it happen spontaneously? It has nothing to do with the rate. Okay? Rate is the world of kinetics, dealing with the speed of a reaction. Okay? And then make sure you're familiar with those 2 definitions below, a spontaneous process and a non-spontaneous process. And to illustrate the difference between kinetics and thermodynamics, let's think about radioactive decay. Okay? Here we're looking at the radioactive decay of uranium-238 and technetium-99. Okay? Both of those are spontaneous processes. Okay? They occur naturally under the given conditions. Okay? They will happen, but if we think about those 2 half-lives, right, our decay in that blue line for technetium has a half-life of about 6 hours. Okay? For uranium-238 decay, that half-life is about 4 billion years. So those are both spontaneous, but they're very different kinetically. Okay? The technetium decay has a faster rate. Another thing to illustrate, okay? Think about diamond. Diamond turning into graphite, which is what's shown on this slide, is a spontaneous process. Okay? But imagine how the value of a diamond ring would change if they all of a sudden just poof, turned into graphite, right? Which is what you have in your pencil in front of you. So we've got some important ideas here. Diamond is actually thermodynamically unstable. Okay? It would spontaneously turn into graphite, but the process would take so long, right? It's kinetically unstable. Okay, so in terms of thermodynamics, could diamond turn into graphite? Sure, it's thermodynamically unstable. Okay? But it takes too long for it to ever realistically happen, okay, so it's kinetically stable. Key ideas, difference, thermodynamics, kinetics. Right. So let's start building towards this idea of entropy. Okay. Let's think about the diffusion of a gas in a vacuum. Okay. If you put a gas in a vacuum, into a vacuum, right, that will diffuse spontaneously. That's something we talked about in chapter 9, when we first learned about diffusion. Now, in a vacuum, pressure is equal to 0. So if we define our work as pressure volume work, again, an equation we saw back in chapter 5, right, work is equal to negative P delta V, well, pressure is 0. Okay? So that knocks that whole term out, right? Work becomes equal to 0. And then because no heat has been exchanged, the value of Q is also 0. And delta U, right, our internal energy is U, is equal to heat Q plus work W. So if those are all 0, delta U is equal to 0, there's been no change in internal energy. So even though we had a spontaneous process with the diffusion of that gas in a vacuum, there was no change in internal energy. So that thought process tells us that the spontaneity of that gas diffusing isn't due to a change in internal energy U, but rather the driving force is simply the greater, more uniform dispersal of matter. And that is a key idea in thermodynamics. Okay, that drives reactions forward. The greater, more uniform dispersal of matter. Right, getting closer to our idea of entropy, just thinking about, right, what that would look like in a figure. Okay, we see the gas spontaneously diffused throughout. Okay. The same relationship is observed with thermal energy as well, right? We learned about thermal energy in chapter 5 as well. Heat spontaneously flows from something that's hot to something that's cold, right? Thermal energy goes from something that's high in thermal energy to low in thermal energy when they are placed in contact until they've established thermal equilibrium and they're at the same temperature. And so on the left-hand side here, they're not touching, but as soon as we put them in contact, thermal energy, shown here as heat, transfers from high thermal energy, the thing that's hot, to low thermal energy, the thing that's cold. And those ideas bring us to 16.2 in this discussion of entropy, okay? Building on these ideas we were just talking about. With the idea of entropy, we want to think about a reversible process. This is some sort of change, a chemical or a physical change that's taking place at an incredibly slow rate, right? Think about the sloth from Zootopia, right? Slow rate, slowly moving, right? Infinitely slow, which means every step of that reaction is arguably at equilibrium, okay? Meaning that the direction of every step in that reaction can be changed. Okay? We can reverse it by any change in conditions. Just tweaking the conditions, a small change in those conditions a little bit would send the reaction back, right? Like a teeter-totter with those equilibrium reactions. Small change would send it back. Those ideas allow us to determine entropy, right? It's kind of a thought exercise, and that gives us the definition of entropy. And as I mentioned at the beginning of the video, that's represented by the symbol S. And entropy is S. So what else do we have with entropy? Okay, we'll tie back on those ideas in the next slide. Entropy, just like enthalpy, okay, is a state function. It depends only on the final and the initial states. It does not matter how you got there, where you started, where you finished. Okay. And entropy relates the spontaneous heat flow we were just talking about of a process to the temperature at which the process is taking place. And if we have an actual real thing, right, a real irreversible process, not the thought exercise anymore, the entropy change for a true process is equal, right, to whatever that would have been for the theoretical reversible process doing the same states. So now we've gone from the theoretical world to the real world because it's a state function. It doesn't matter how we got there. If it was a whole bunch of tiny steps that were reversible, one big jump, now we've tied together those two different worlds. Okay. So how does that look in a formula, right? Delta S, the change in entropy, is equal to Q sub ReV, that's the heat of the reversible process, over the temperature at which it takes place. Okay, so S is entropy, Q is heat of the reversible process, right, in joules, T is temperature in Kelvin. And we can tie entropy together. This is getting into the world of physics, now closer anyway into the world of physics. Maybe you've heard of this, maybe you haven't. Right? We can relate entropy to the number of microstates of a system. What does that mean? What's the definition of microstates? These are how many configurations we can have for the atoms and molecules that our system is made up of, both where they are and how they're moving around, right? How much energy do they have? Because remember, atoms and molecules are always in movement, right? They're tumbling, they're moving around, and they're vibrating in their individual bonds. So we're thinking about where they are and how much energy they have. And if the number of microstates, okay, the number of possibilities increases, then the overall entropy of the system increases. Okay, so if the number of microstates goes up, which is the number of possible configurations of locations and energies, then the entropy has gone up. That brings us to another formula here on slide 14. How do we calculate that? Delta S, change in entropy, is equal to S sub F minus S sub I, final entropy minus initial entropy. Okay, and we can relate that to work from before. Okay, we've got K natural log, a whole bunch of formulas. The textbook goes through defining all of them. The only thing that I'm going to want you to know, okay, from this slide is what we've got right here. Okay, delta S is equal to final entropy minus initial entropy. You don't have to worry about what's going on over here. A little bit different from the book. You also don't need to know the equation derivation and the microstate probability that your textbook talks about. Okay? But if the number of microstates goes up, right, getting into the world of theoretical physics, you can see C there, highest number, the highest probability of our 16 microstates having things, 2 particles in each box. Right, those are all the possible microstates for having 4 particles in those 2 boxes. You don't have to know about all the probability that the textbook goes into, but you do need to be able to predict a change in entropy. That's a big idea from chapter 16. I will ask you to do that. Predict a change in entropy. Is it going up or is it going down? And that's easiest to do. What you're hoping for is just by detecting a change in a number of gas particles, for example. Because if we increase the freedom of motion of our particles, and they can move about more, then the number of microstates naturally increase. Because remember, microstates dealt with both energy and location. So if things can move around more locations, right? So that tells us that the entropy of a gas is therefore higher than the entropy of a liquid, which is higher than the entropy for a solid. There, as you increase the number, right, you go from a liquid to a gas, you go from a solid to a liquid, you go from a solid to a gas, any of those would increase the overall entropy of the system. Okay, and your phase changes in between those. We talked about those earlier in the semester, right? Those have corresponding entropy changes as well. Okay? And that's just shown in this slide right here. If we go from a solid to a liquid to a gas, our entropy is going up. If we're doing the opposite of that, our entropy is going down, right? So if we freeze water, for example, it's gone from a liquid to a solid, its entropy has gone down. What about the energy of those particles? Thinking about vibration and the relationship to temperature. Okay? If we tie back to kinetic molecular theory, that KMT from chapter 9, we saw at the end of chapter 9, right, that the temperature of a system is proportional to the average kinetic energy of the gas particles. As the temperature goes up, the kinetic energy goes up. Okay, both the average kinetic energy and the distribution. So if I have a higher temperature, then that should make sense. That's putting more energy into the system, right? That means my atoms and molecules are moving around faster. They have more vibrations, and therefore entropy increases with temperature. Another big idea, right? So we're looking at the phases, right? If I've got more gas or liquid than what I started with, then that's going to be a positive entropy. Now, if I'm heating the system, that's an increase in entropy. Okay, that figure on the left is what we saw in chapter 9, right? As we increase the temperature from T1 to T2, my average kinetic energy has gone up, right? My average value, but so has my distribution. And as I go from T1 to T2 there, I've increased my temperature, I've increased my entropy. And at my phase changes, this should look familiar as well. Those will have corresponding entropy changes as well. See how it shoots up, right? Because that's when all my particles are changing phase. So that wraps up our discussion of entropy. Okay, we will pick back up with the next video, jumping into the second and third laws of thermodynamics.